we basically, what we did was we did the sentiment analysis by the way of using the word embedding from the Google. And we did the sentiment analysis on the movie reviews on IMDb. All right. So that's a very, very interesting example because there are libraries out there which help you do the sentiment analysis, but that do not give you the power or the capability of doing all kinds of magic on the data. The approach that we discussed yesterday is very useful when it comes to doing the language processing and can be utilized in many more ways, right? Let's say you want to train a model which fits a sentence or captions an image, right? Image captioning. The same strategy can be used there. There you will feed the image, you will feed the captions, and or you let it predict the words, and then you basically um, utilize the same mechanics that we talked about. All right. So image captioning, or there could be 100 things or many kinds of applications of whatever we have learned so far in CNN and RNN. All right. So moving ahead, so we talked about the normal RNN so far. Now in RNNs, there's something called bidirectional RNN. Bidirectional RNNs are nothing but two RNNs, one starting from basically two RNNs. In one, you are feeding the sentence, the sequence from beginning to end, and the other, you're feeding the sequence from end to the beginning. All right. So some of you who were not comfortable with the idea that why are we feeding milk, drink, I, right? There was a valid reason, because you never know, there could be another language in which the last word is most important, right? Last word is more important, not the first. In that case, we have to feed it from the beginning. Now, question is, why should we try to do it? We let the system decide that. And how to do that? Instead of having an RNN like this, we'll have two RNNs, one like this, and other just basically we'll have two parallel RNNs exactly like this. One is this RNN, other, and we basically join them like this. In one, we feed milk, drink, I. Other, we feed I, drink, milk, and then we concatenate the results. All right, that's called the bidirectional RNN. Okay, so bidirectional RNN, like to encode properly the word queen in Queens of the Queen of United Kingdom, right? The Queen of Hearts, the Queen Bee. You need to look ahead, right? You need to look ahead. You need to know the data from both directions, and that's where the bidirectional RNNs are very useful. So the inputs are same, just that in this one, there are two RNNs at the work. First one, we are feeding X0. Then the second value in the same RNN, we are feeding the X1, then X2. While the another unit that we have in which we are feeding X2 followed by X1, then X0. And the results are being concatenated. So Y0 is the result of this and this. Y1 is a result of this and this, right? And so on. So this is a wonderful way of operating upon it. So it basically detects whether your language is left to right or right to left. Okay. And it essentially concatenates. Sometimes in some of the neural network, instead of concatenating the result, the result will have two outputs, Y0, Y1, Y2, and then one with respect to this neural network, other with respect to the other neural network. So it'll have two-dimensional output. Okay. Now, keeping that aside, in certain cases, instead of concatenate, people prefer to even add these values and so on. All right. So basically, this is bidirectional RNN. In some of the cases, bidirectional RNNs have proven to do pretty well. Okay. So there are two RNNs. The results are being concatenating the results, and that's about it. Okay. So you can implement the bidirectional RNN in a very simple manner. I'll just show you. Okay. And here we go. All right. So there we go. Let's just move ahead and we'll come back if we need to basically use it. So it's pretty simple. All you need to do is we just add bidirectional here. Okay, we did not do anything. We just added bidirectional here, and essentially it resulted in twice the number of neurons as compared to the first one. You notice that? Twice the number of neurons. And the output shape has 20 values, though we have 10 neurons here. Why 20? 10 from one and 10 from another. It's basically being concatenated. So you can see that this result is uh, based on the concatenation of the two. Okay, and that's about the bidirectional RNN. Okay, that's about the bidirectional RNN. All we have to do is wrap any RNN into bidirectional, and that becomes bidirectional. Also notice that in case of bidirectional, total number of neurons are not 10, they become 20, right? There are 20 outputs, as well as the total number of weights are going to be doubled, right? Because they are essentially two separate neural networks. Cool. Now, there are a few more things to know about the model that we encoder decoder model. In encoder decoder model, first thing we talked about is the bidirectional RNN, because instead of we deciding whether the language to be fed from left to right or right to left, let the neural network figure it out. Okay, let the neural network figure it out, and that's why there are bidirectional RNN which perform better than the normal RNNs. Okay, now the next thing is, how does the prediction work? How does the prediction work? Okay, I'm going to explain to you that. So when we are doing the translation from one language to another, what we want to do is when somebody said comment was to Jor, it should be converted into how will you play, right? This translation has to happen. Okay. And this is the encoder decoder model. Now, we are not going to predict the entire sentence in one go. Instead, we will predict one word and then we'll feed that word to the next one and then predict the next one, then feed the next one and so on. So that way it'll be a cyclic. Okay. So first it will predict how, then will, then you, then play, right? And notice that once we are done with predicting how, the will be fed to the same network. Now, there's a very interesting thing. Neural network is not going to give you the word as such. Instead, it will give you the probabilities of words. Imagine that there are multiple suggestions what to do in those cases, right? So in that cases, we use something called beam search. Okay, beam search. So it keeps track of k number of suggestions at every point, and using those k number of suggestions, we keep on feeding it back. All right, this is something important to all of you, and you will see this kind of strategy in other situations as well. Like when we talk about reinforcement learning, we will also have a similar mechanics there. Okay, so coming back to it. Now, what it does is it is basically the beam search is essentially used at the time of prediction. All right. So beam search, though it is used at the training time also, but we will focus more on the prediction time. Or you can say that we will basically call the same model over and over, and we will keep on picking only few things. Okay, let's just walk through the example and then you'll get an idea. It's a pretty simple thing. Okay, so what we do is at every stage, let's say we trained a model and the model is doing very good. To this model, we gave this sentence called comment was to. That's the sentence we have fed to this model. Now, this model has given us an output called the three suggestions are the most predominant. But let's say it is giving us 10,000 such outputs, right? Because we are predicting the probability of 10,000 words. We are predicting at every step the probability of 10,000 words and picking the words that are most popular. So instead of picking single word, we pick here 3. The beam search width here is 3. So we are just picking 3 most probable words. Okay. So how is 75% probability? How has the 75% of probability as the first word of the result? So we are feeding this comment. Okay. Here, this comment, this text is being fed to this model. Now, when we are feeding this text to this model, it is giving us, once we are done feeding one word at a time into this encoder decoder model, it will give us these 10,000 outputs. These are 10,000 outputs. Okay, along with the basically probability of various words. Okay, so it's saying that the how should be the chances of how as the output is 75 and what as is 3 and u as 1. So we pick most probable 3 results, right? So how, what, and u is what we have picked. Now moving ahead, what we're going to do is we're going to feed this how now into the same model. This model and this model are the copy of each other. Okay, these models are copy of the same one, right? It's the same model. It's a copy of the same model. Now, in this, we are taking how, feeding it to model. Now, how many results will model give? Anybody? Notice this, that the model gives 10,000 results. Yes, thank you, Vinod. Thank you. Okay, so model gives 10,000 results, correct? Width is still 3, that's correct, Pridesh. We are going to pick only 3. We are going to pick only 3. So here, 10,000 here, 10,000 here, and 10,000 here. So how many total results will be there? 30,000. A question from Domenico is that don't we pick 3 into 3? No, we will pick overall 3 only. I'll explain to you how. Okay. So each model is giving 10,000 results, and total we will have how many? 30,000. Now, each probability of this, let's say the model is saying the probability of will is 0.36, as in 36%. R is 0.32. Do is 0.16. So overall probability of how and will is 0.27. How and R is how much? 0.24. How do is 0.12. Correct? Clear? We are basically multiplying the individual probability with how, because we will go to this root, right? So the probability of how multiplied with this, right? Remember the conditional probability? This is how it works. So reaching how is 75% probable. So reaching will be 75 multiplied by 36% and divide by 10,000, right? As in because of the denominator. Okay. So now you see that. This sentence has this probability. This has this. This has this. This way there will be 30,000 results. Okay. There will be 30,000 results. So there will be total 30,000 such numbers. From this, we will just pick top 3. A question from Srini is, are you sending how and the full sentence to the next model? We have already fed the full sentence to the model. Okay. I mean, we are assuming that we have already fed the full sentence to the model, and now we are only feeding how. Okay. Or you can just assume that if we are taking a pristine model, okay, we will basically, again, at this step, what we're going to do is we are going to feed this followed by how, right? Similarly, we're going to feed this followed by this. Okay. Then similarly, we're going to feed this followed by you. Okay. That's what we're going to do. For the visualization, we are showing that this model, we have already fed this. Okay. So it's ready to produce. And then when it starts producing, it gives these words and we again feed it back. All right. Okay. Question point from Srini is that can you please repeat? All right. So we have a encoder decoder model, right? We have trained it and we are happy with the training. Now, once we have trained the encoder decoder model, it's a time for prediction. And this model predicts 10,000 probabilities because there are 10,000 possible words as the outcome. And since we are using softmax, the 10,000 out of those 10,000, the total probability of all the words is going to be 1. And we are going to pick only top 3. Okay. So we fed command was to this model. This model gave us 10,000 such output, right? The probability of how is this, what is this, you is this, and we pick only the top 3. So we picked these. Now this is being fed to the same model, which is a copy of this model to which we have already fed this. Now this how is being fed to this model. In case we can't copy it like this and we are loading the weights, we will have to feed this. Thank you. Thank you. I'm not Koma Vatu. Thank you, Santosh. So yeah. So when this French sentence is being fed, so we have already fed it. We make a copy after feeding, or if we can't make a copy after feeding, what we have to do is we have to take this, feed it first. This is the first thing we are feeding. And the second thing we are feeding is how. Similarly, this is being fed here 1 and what as the second. This is being fed 1 and this. Okay. So if this model, right, is on the same machine and we have just copied or cloned the entire state of the machine, state of the model, then we don't need to feed it again. Here at the training time, all right, at the training time, what was it that we were doing? Yes. Okay. So we were feeding this as well as this, and we were getting these probabilities, right? So in case of prediction time, we don't feed this. We do not feed this. Instead, we just feed this part. Okay? We just feed this part. And once we are done with feeding this part, we will get this first word. And then this word will be fed back. And then we'll get this word. Then we will feed it back. Then we'll get this word. Then we'll feed it back. And we'll get this word. Then we'll feed it back. And we'll get this word. Okay. The important part is that in case, let's say you are doing it distributed way. Okay. Just let's assume for time being, let's say we are doing it in a distributed fashion. Now, the distributed fashion, and in the sense that all the models need to be reinitiated. Okay. In that case, we will have to again, let's say the model is pristine and we haven't fed any input yet. In that case, we'll have to fed it again and then fed the previous value that resulted. Okay, so that way. All right, if this model is not a copy of this, is not having the same state as the one where we fed this value, then we'll have to feed it from the beginning. Okay, so I hope this is clear. From this, we'll basically pick the top 3, this and this and this. These are the top 3. And after multiplying this probability and this probability, we basically are getting a number and we're picking the top 3. Okay. And we continue this. Notice that every step, we have only 3 values left. Okay. Why 3? Because we have chosen for the visualization purposes, the width is 3. So we will get many possible sentences, but after a point of time, the sentence will become more and more meaningful as we go ahead. Okay. And the one at the end of it, the one that has got the highest probability, we basically stop there. Okay. Like if we are having a bigger sentence or we are predicting, it would predict like end of the word at some point of time, and then we will stop at that point of time. Okay. Right? So in case of TensorFlow, this is part of TensorFlow add-on, TFA, the way we have imported it, right? It's essentially, this is the kind of the search encoder it is. So we basically call Beam Search encoder like this. And here we are saying what is the URL of the decoder cell, beam width, and the output layer. Okay. Why decoder cell? Because the previous word will be fed back to the decoder cell. Okay. The previous uh, outcome will be fed back here. All right. And decoder, this is decoder. And the initial state is we take the beam search decoder, and we basically give the encoder state here. The example that we have given, and that's about it. So essentially the important part is that knowing what exactly is beam search, and then based on a product that you're using, whether PyTorch or TensorFlow, you can take a look at the API and use that out of the box. Okay. Or you can code your own. That's not a big deal. You can code your own if you know how to call your neural network with the input, and then how to extract the output from it, and so on. So you can code your own, or you can design your own neural network if you know the fact that if you know the mechanism of the beam search. All right. Now, again, the RNNs, no matter how good they were in as compared to the other models, RNNs were way better than any other model in keeping sequence of time. Okay.